its ramifications. So I think we're going to get one of these ramifications today.
Looks like a ramification.
He's also editor of the World Science book series on knots and everything. So if you've got anything at all you want to get published, then Lou is your man. The other very interesting fact I found in Wikipedia is that Lou plays the clarinet for an orchestra called the Chicken Fat Klezmer Orchestra. Is that right? In Chicago.
Yeah.
You bring your clarinet with you to Cambridge?
I did, yeah.
Well, you see, wonderful.
Maybe we
may hope
some
for a
concert.
we may hope for a concert before the end of this program. Anyway, here is Lou and his title, Quantum Information, the Jones Polynomial, and Khovanov homology. Lou.
Okay, so this title is slightly different from what I had advertised, and the content is slightly different from what I'd advertised. There's a large amount of overlap between the content of what I was telling you I was going to talk about in this. It has to do with the theme. One of the themes of this talk is how the Jones polynomial is related to quantum information and how you might design a quantum algorithm to compute the Jones polynomial. It turns out that the Jones polynomial is actually very centrally located to quantum algorithms, and I'm not going to talk about that part exactly the way I would have before. I'm just going to talk about how to formulate the Jones polynomial in a quantum way. That's one of the themes of the talk. And I think that's interesting in its own right. The way one gets it related to some deeper things about quantum information is by way of braid group representations. And that's another talk. So that's why I decided to separate this out. And then there is an extension of the Jones polynomial called Khovanov homology that was discovered by Misha Khovanov around 1999. And that turns out to fit into a quantum context also in an interesting way. And all of these things have to do with the theme that the Jones polynomial is related to statistical mechanics. So I'm going to start with something that won't happen in the talk again until near the end. Here is a picture of the Ising model, a simulation of the Ising model near criticality. And as you know, the Ising model is a two local state model of a physical system, usually done on a large rectangular lattice. And the problem, original problem about the Ising model was to see whether or not it had a phase transition mathematically. And this was solved after a long time by Onsager in the middle 1940s, and the solution is quite complex however you do it. The model itself is very simple. You just have vertices on a lattice which are assigned a spin or a charge, a plus or minus 1 or 0 or 1, two different local states, and an energy that I'll say later for each state. And then one has the partition function which sums over the exponentiated energies in a certain way. As I say, I'll come back to that. And then the question was whether this partition function in the limit as the size of the lattice goes to infinity, whether it had a clear phase transition. So one of the features that you see when you look at a simulation or an actual physical system for that matter, but in a simulation of this kind of a model, is you see regions of constant, I'll call it spin, the two choices, the black and the white. So you see a lot of regions.
This is a
Comment?
2D and 3D.
I'm sorry.
It's three-dimensional, two-dimensional.
This is two-dimensional. Yeah, this is a two-dimensional Ising model. It was solved in 2 dimensions by Onsager. It's still an open question about solving it in 3. So these are complicated problems based on very simple models. So you see a lot of regions of constant spin, and then regions within them of the other spin, and so on. If you were to draw a sketch of this, you would draw a lot of loops. You would draw, I'm sorry, yeah, there. You would draw a loop which went all the way around the boundary of this, and then inside that you would draw a loop around this, and so on. And you can look at this and see a configuration of nested loops, and that configuration of nested loops describes the situation of the regions of constant spin. Quite complicated near the critical point, even more complicated to the point of being chaotic when you raise the temperature, and when you lower the temperature, the regions become very, very simple. So that's a picture of how the Ising model looks.
Chaotic in what sense?
I don't necessarily mean chaotic in any technical sense, just patternless. This is repeating what I just said. And then here's the thing. There is a generalization of the Ising model called the Potts model, where instead of having two states, you have any number, some integer number of states locally. Otherwise, it's exactly the same model. And that one turns out to be related to the Jones polynomial and to some graph theory, and I'll come back to it if I have the time. But in those techniques of looking at it and relating it to the knot theory, it's very natural to rewrite everything in terms of exactly those configurations of loops that I was indicating to you. So in back of something you do with the knot theory are these configurations of loops, which we're going to see in the knot theory. And in back of that is the question, well, if you did something involving those configurations of loops that was mathematically interesting, and that's what Kauffman homology does, it does something mathematically interesting with those loop configurations, then how should that be related to the statistical mechanics? Or for that matter, can you think about the statistical mechanics in terms of the structure of these loop configurations? So that question is in the back of my mind as I'm telling you about knot theory in this talk. But I'm going to tell you about knot theory for the most part in the talk and making it into a quantum formulation of the Jones polynomial and how to make a quantum algorithm for the Jones polynomial and all those things. So they don't require the so much of what I say is a way of talking about Kauffman homology and talking about the form of the Jones polynomial. The quantum mechanical framework that I'm using doesn't actually necessarily speak to the statistical mechanics model that I just mentioned. So that's our agenda: quantum information and some things about knots in physics. Now comes a section of cartooning, particularly as you'll see in a moment, because I got curious about what would happen if I looked up Schrodinger's cat on Google. And you could spend some happy time playing with that if you want to yourself. This cartoon on the left is due to John Wheeler, and the one on the right is due to me. The one as a takeoff on John Wheeler's cartoon. John Wheeler's cartoon is a picture of the universe as a letter U, observing itself, and in fact observing back to the, I'm not very good at finding out where the, maybe I'll just use the other one. Just a second. There. Going back to, looking back to the Big Bang, you see here's the Big Bang and the universe is expanding, and it finally got enough structure to be able to observe itself, and it observes the Big Bang. Wheeler liked to present this as a kind of quantum paradox. So what's the paradox? Well, according to orthodox quantum mechanics, a phenomenon is not actual until it is an observed phenomenon. Otherwise, it's in a superposition of possibilities, but it's not actual, which means that if you took it literally, the universe itself is not actual until it manages to be able to observe itself, which seems to be a paradoxical situation. This is a kind of generalized Schrodinger's cat paradox in its way. I knotted the universe because I like knots, but also because I wanted to emphasize for myself the question of contextuality. Knots are about contextuality. What is the contextuality in which you make this question about the universe? What is the contextuality in which you talk about a string of rope? And the string of rope in the abstract has no structure like this knotting. The knotting depends on the way the rope is embedded in three-dimensional space, its context. And in that context, there is an infinite complexity of things that can happen. But as I said, this is the cartooning section of the talk for a couple of minutes. And it starts with Wheeler. But then, as I said, there is Schrodinger's cat, and I thought I would just show you a couple of the ones that I liked that I found. This is, this one, as you see, has the box in Rube Goldberg form with the possibility of the quantum event triggering the jar of cyanide and killing the cat, who seems to be worried. And then we have Schrodinger possibly observing the box, and we have Wigner observing Schrodinger. And this really should be another box around Schrodinger for this problem about Wigner's friend. Because, as you know, if Schrodinger were in an outer box observing, and then the cat would be alive or dead for him, the wave function would have collapsed. But Wigner, not having opened the other box, would still be having a superposition, in this case of Schrodinger with cat alive and Schrodinger with cat dead. And that's the most abstract cartoon I found, a superposition of a live and dead cat. And this is one of the reasons why people find this so fascinating, because they find this ambiguity mixing with other sorts of ambiguities that that everyone is interested in, such as perceptual figure ground ambiguities like this one, or ways of making superpositions artistically. Does that work for you? I was curious to see whether it would when it was magnified. There's a kind of an uncertainty in this illusion. Yeah. It's not working for me, but I'm off to the side of it. Those are perceptual uncertainties. And then there's, of course, the Cheshire Cat. And then then I found, with some amusement, a quantum cat thinking about quantum mechanics. And the reason I was amused by this is because it gave me the opportunity to steal a slide from my collaborator, whom otherwise I would not insult by stealing his slide. But Sam Lamonaco always uses this quantum dog in his talks. And so I felt that I had the right, having found the quantum cat, to use the quantum dog. And then getting back to the quantum cat, this is the last one, almost. I found this nice title, Zeus-like title. And then, of course, there are illustrations like this. And let's stop here and go back to work. Here's Schrodinger's equation. And you might, if you learned quantum mechanics long ago, like I did, or tried to learn it long ago, think of this as the signature of beginning to learn quantum mechanics, studying that equation. And when people studied that, when Schrodinger found this equation and when it got studied, it became clear almost immediately that certain things were invariant under time. And in particular, the integral of psi times its complex conjugate, psi star, the integral of psi star over space, is time independent here. That's an inner product in the Hilbert space of functions psi that solve the equation. And so one then thinks of the quantum state psi, the quantum state psi is representing the physical system, and the inner product of psi with itself is constant, so that means that the time evolution of psi is unitary, and one can interpret psi as psi star as a probability density, and so came the probabilistic interpretation of quantum mechanics. And of course, the unitary evolution depends on the structure of this equation. But if we want to abstract this and just talk about quantum mechanics as a model in a more rarefied way, we can say this. And here I think of the vector spaces as being possibly finite dimensional, because that's what one tends to do when one is doing quantum information theory. And it means concentrating on some particular kind of observation, like it might be the spin of the electron, and that's all you're thinking about. So in a nutshell, the abstract description is that the state of a physical system corresponds to a unit vector in a complex vector space. I'm using Dirac's ket and when you put it in the other form with the arrow going the other way, that's bra, and when you put them together, which I didn't write here, but somewhere I probably will, you get the inner product. And when you do reverse the arrow direction, you conjugate. So if I have a vector here, z1 times a basis element plus zn times a basis element, then its psi star, its conjugate, has z1 bar, z2 bar, zn bar. And of course the inner product, if these are orthonormal to one another, which I have intended them to be, is just the sum of the absolute squares of the zi's. So that's what's preserved. And in this model, the probability of getting one of those directions as in your measurement is the absolute square of the zi. So probability is equal to 1, and when it undergoes a physical process that doesn't involve observation, the probability remains totally 1, and the different emphases of vectors change. So with this abstract description, you can, if you're inclined mathematically to try to make a unitary transformation that does something interesting, just go ahead and design one and not worry about whether or not you can implement it physically. This is the computer science enterprise of doing quantum information theory. And one of the nicest successes of that was Peter Shor's algorithm for factoring numbers, where he indeed designs a unitary transformation, composite of certain unitary transformations, which when you start the system by applying it and then measure it and then do this again and again and again, the statistics of the result can tell you about whether a number is factored and how it's factored. So this is quantum mechanics in a nutshell, just this statement that physical processes are modeled by unitary transformations, and that measurement consists in the projection into one of the possibilities in the measurement basis with probability the absolute square of its coefficient. And in order to actually have a real physical process that corresponds to this, you have to go more deeply. But if you want to think mathematically about something and put it into a quantum framework, you can just follow these rules. In particular, here's an example. This is the Mach-Zehnder interferometer example, very well known. There are two mirrors in the example. One, the black one, is an ordinary mirror that just reflects, and the other one is a half-silvered mirror. It transmits and reflects. When a particle of, I'll call them spin 0 and spin 1, just to have a name. So when a particle of spin 0 goes into the half-silvered mirror, out comes a superposition of 1 and 0 equally. So if you set it in terms of matrices, that would be h applied to 0 is 1, the vector 1 times, the vector 1 plus the vector 0 divided by the square root of 2, and represented in coordinates as 1 and 1 in that column. If 1 goes into it, out comes a superposition of 0 and 1 with a phase change on the 1, and that makes the transformation h that I have illustrated below here unitary. If we didn't have the little phase change, it wouldn't follow the rules. It wouldn't be unitary. So you see how certain little physical aspects follow from having to follow the rules. And then the other mirror just interchanges the vectors. So the process here is to go through the half-silvered mirror, then go through the mirror, and then go through the half-silvered mirror. And that corresponds in our model to taking the composition of h and m and h, which if you multiply them out gives you this, and says that you have absolute certainty of having 0 come out if 0 went in. So that's an example. In the example, you see something else. There's another way of thinking about quantum mechanics that's very useful, which is to look at the apparatus and think about all the possible paths that the particles could take as they wandered through the apparatus. And here, we could add them up quite easily because there are just a few paths, and we see that there's a destructive interference on the 1s and a constructive interference on the 0s, and it matches exactly what happened when I multiplied matrices. But in this finite dimensional case, this is not at all unobvious. It's completely obvious, because when you multiply matrices, what you do is you take the combinations of the outputs of one and the inputs of the other, all possibilities, right? And that's what happens here when you multiply these matrices. So matrix multiplication automatically gives you the path sum interpretation of quantum mechanics if you started with the model that we had on the previous slide. Of course, then if you want to take a limit into infinite dimensional spaces and Schrodinger's original equation, you have another problem. And that's the problem of making sense of the path integrals. And also you get more physics coming in when you start to think about that. But the path integral interpretation or the path sum interpretation is part and parcel of the matrices. So that's an example, and I'd like you to take away from this matrix, which people in quantum information theory like to call the Hadamard matrix. So here's an example of a quantum computer that I'm interested in, an abstract quantum computer. My question is, how do I get the trace of a unitary transformation? As a black box, without looking inside, of course. So it's thought of as a quantum process, and I want to get the trace of the unitary transformation. So that means that what I'm after is psi u psi, phi u phi, where phi is some vector, right? Could be a basis vector, or I could change basis. I'm interested in these diagonal matrix elements, this guy here. And I'm going to build a little machine that's going to determine this number, 1/2 plus the real part of phi u phi divided by 2. The machine is built in the following way. I start with u, which is given to me as a process. I form a new process by putting an extra tensor line and making a controlled u. If there's a 0 on this line, this is going to be the identity. But if there's a 1 on this line, it's going to be u. And now the space of inputs, the preparations, are larger. There is things of the form 0 tensor something and things of the form 1 tensor something. Here's a Hadamard. Now this is the machine. So this is one of the unitary transformations in the machine. Another one is putting a Hadamard on that extra tensor line before and after, and then making a measurement. So that's the process. I start with 0 tensor phi, and then I apply this process. Apply Hadamard, apply the controlled u, apply Hadamard again, and then make a measurement. And watch the frequency of 0 under the measurement, because things that come out will be of the form 0 tensor something plus 1 tensor something. I want to know when I measure with what frequency do I land on the one with the 0. And that frequency turns out to be this. The way you do that is by doing a little calculation of the vectors involved and then the inner products involved. And rather than say anything about it, I'm going to use maybe 5 seconds and show you what it looks like and go on. So there's the Hadamard, and then here's the algebra of applying the controlled u, which in one case applied a u and in the other case didn't, and then doing the other Hadamard and doing the inner product and finding the result. And then you can do the same thing with an I in the system and get the imaginary part. So that's a lot of work from the outside. It looks like a lot of work to get at the trace of this matrix. But that's a typical quantum computer. In the abstract, you build it this way. In practice, you would have to repeat this process of measurement many, many times in order to get at the statistics of the result. Or you would have to use some kind of system that works in big parallel, like the NMR systems, where there are many, many molecules that are all doing the same job. And then the repetition could happen in a certain sense all at once. And NMR systems can be used to do a little quantum computing. With a group of people, we worked, there's Sam and others, we worked on trying to compute the Jones polynomial using NMR, and we can do it for some very small things. But this kind of system is fundamentally limited. So, and in fact, every system that people have so far tried has been limited, but we don't know. Maybe in a little while there really will be quantum computers that people use. Now I want to go to the knot theory. So a knot is an embedding of a closed curve in three-dimensional space. two knots might be equivalent even though they don't look equivalent. Here is the trefoil knot in its usual form, and over here on the right is another version of it. And these are just two torus knot versions of the same knot. One is the 2 times around one way and 3 times around the other, and the other is 3 times around one way and twice around the other. And you can see that you can see mathematically that these knots are equivalent to one another by simply interchanging coordinates. So you might see without seeing. In order to see in a more direct way, you would have to think of deforming one into the other, and maybe you've done that in your mind already, or maybe not. It's not so easy to do those deformations. Abstractly, two knots are equivalent if there's a homeomorphism of three-dimensional space to itself that carries one to the other, and orientation equivalent, space orientation equivalent if that homeomorphism is orientation preserving. So we tend to think about knot theory in two ways. One is looking for homeomorphisms like that, and the other is thinking about doing a deformation from one to the other. For example, is this knotted? Is there a homeomorphism of three-dimensional space that throws this to an ordinary circle? Or can you twist it until it becomes unknotted? Opinions?
Yes.
Yes, it's knotted.
It's unknotted.
Yes, it's unknotted. Sometimes people see this. I'm not good at seeing that this is unknotted, but it is unknotted. If you want to see a deformation of it, I'll do it later. Here's one last cartoon, actually. This cartoon is from the Scientific American article from a few years ago about topological quantum computing. And there are some nice themes in the cartoon, so it's worth staying with it for a moment. There's a braid. The braid seems to be controlled by a person up there. There are these vortices down there, and strands of the braid correspond to these vortices. So the vortices are an artist's depiction of collective excitations of electrons in the quantum Hall effect in a flat plate, which can be regarded as quasi-particles, and they move around one another and can braid with phases that occur in the quantum mechanics. So there is a hope that one could use that quantum Hall system to do quantum computing by being able to somehow measure the phases that go on. And then one would like to control it, make unitary transformations, compositions of them that correspond to compositions of elementary braidings. So this picture contains a lot of ideas and hopes. Now getting back to the knot theory proper, as I said, one doesn't have to think about homeomorphisms. One can think about moving the knot around. And if you combinatorialize that, you get the following 3 moves. Reidemeister got the following 3 moves in the 1920s, which give a combinatorial depiction of isotopy of knots in 3-dimensional space. 2 knots are equivalent if you can get from one to another pictures of them by moving the pictures around by these local moves. Local moves consist in the graph, a loop in the graph, a 2-sided region in the graph, or a 3-sided region in the graph that is changed locally according to the moves. Each one of them is obviously an isotopy of knots. What's not quite so obvious is that any 2 knots that are equivalent, if you take snapshots of them, can be transformed one to another by a sequence of these moves. And I put a different subject over here on the left, the well-known photograph of knotted DNA from the 1980s due to Cosarelli, Spengler, and Stasiak. I like to think of this picture as a triumph of knot diagrams in science, in as much as the only way you can interpret this is by thinking of it as a knot diagram, and then looking at it as a knot diagram, you see that it is woven. And of course, it's a very difficult experimental procedure to get the DNA into this condition. The other one is the well-known Borromean rings, which are linked, but any one of them removed and it's not. We want to talk about the Jones polynomial. So I'm using the bracket model of the Jones polynomial, which you can think of as a recursion, which applied to a given knot diagram associates two other diagrams to it by taking a crossing and smoothing it one way or smoothing it the other way. So you have diagrams, I'll have an example in a moment, which are the same except that these two at this local site where it's been changed in two possible ways. And then the invariant is equal to the sum of the invariant of one times A plus the invariant of the other times A inverse. And if there's an extra loop, it multiplies by that algebraic factor that you see there. This is invariant under the first two Reidemeister moves. If we had just used an A and a B and maybe a D, then it wouldn't be invariant under Reidemeister moves, but it would be a well-defined function into polynomials on the knots. As I say, it's not invariant under the first Reidemeister move, but it multiplies in a nice way like this, or like that, depending on the character of the twist. So one can, if one wants, multiply this whole shebang by a power of minus a cubed and make it invariant under all three Reidemeister moves. But for our discussion, I'll leave it in this raw form. So here's an example. You start with the trefoil knot, and you take one of the crossings here, and you smooth it one way, or you smooth it the other way. In this case, when you smoothed it one way, the A way, you found a link, hop link. And when you smooth it the other way, you've got an unknotted circle, but it's got some twist in it that we have to keep track of. So then, if you continued calculating this, I give you the answer. This is what you would have found, going all the way to the bottom. And over here, this one, according to the rules in the previous slide, multiplies by minus a to the minus 3 twice, and so gives a contribution of this. And therefore, the polynomial as a whole is this one. And if you were to normalize it, as I suggested, you would find that it tells you that the trefoil knot is definitely not knotted, and definitely inequivalent to its mirror image. So that's how this method works. If you want to think about the method in general, oops, I don't want to do that yet. If you want to think about the method in general, of course, it falls into all the different possible ways that you could have smoothed the knot diagram. And in fact, you can turn it around and rewrite the way to calculate it in terms of all the different ways to smooth the knot diagram. The algorithm then becomes, consider all the 8 ways of smoothing the knot diagram. In this case, there are 8, in general 2 to the n, where n is the number of crossings. Consider all of them. I've drawn them in brackets at the bottom of the slide. Label each smoothing according to the type that it is. And then you can read off the polynomial by walking through and adding up. The first one is a cubed times the value of the loop squared, but I tend to divide by one loop value. So a cubed times the value of the loop, a squared b times the value of no loop, and so on. And each one contributes a bit of algebra to the polynomial, and you add them up, and there's the polynomial. Each contribution is a little bit awkward because suppose you had one with 3 loops. Then in the way I let's just say you take the power of the loop, and I won't worry about uncounting one of them. So if it has 3 loops, then you have to have that binomial minus a squared minus a to the minus 2 raised to the 3rd power multiplied by the weights. So you get a little clotch of polynomial from each one. That's the way it looks. And in that form, it looks like a statistical mechanics model where you're summing over states. But the states, as I said, if you were to rewrite this in the form of a Potts model, the states are actually summary states. Each one of these states would correspond in the Potts model to all of those states in the Potts model that have that particular configuration of regions of constant spin.
Whether this loop expansion is independent on number of states in Potts model, it should boundary is not the same.
Yeah, the form of this, the form of this is independent of the Q in the Potts model. Yeah. If we were writing a Potts model, and that's exactly because these do not speak to the Q directly; they speak to the form of the configuration of states. So that's the way it looks. Oh yes, so let me go back now. For algebra convenience, I'm going to change variables. So you could just read this if you like, as I originally told you that the bracket was given in terms of Q, and it was written this way. And you'll notice it makes the algebra a little simpler, because instead of having minus a squared, I have a Q, or instead of having minus a to the minus 2, I have a Q. But it's hard to tell from there. I just have Q plus Q inverse for the value of the loop. But then smoothing it in the A way gives me a 1, and smoothing it in the B way gives me a minus Q. This is a translation that lets me go back and forth, because it actually corresponds to multiplying the whole thing by a certain power of A. But this turns out to be easier to handle algebraically, so I will stick with this one. And then I'm going to make a Hilbert space, because remember, my aim was to put this in a quantum context. So I'm going to make a Hilbert space whose basis is the set of enhanced states, which I haven't defined for you yet, of the bracket. So this looks like the Hilbert space, except that each one of these actually corresponds to a number of things in the basis that I'm about to tell you. Now, I wouldn't have made the enhanced states, which I haven't defined yet, if it weren't for the fact that basically each one of these has a coefficient, right? Like this guy. He has a certain coefficient that corresponds to how I evaluate the polynomial. The loop squared times A times B times B. And that thing is not a monomial, and it won't stay on the unit circle. And if I tried to make a transformation of the space by taking each one of these to its coefficient times it, the transformation wouldn't look very unitary. And remember, I would like a unitary transformation that models the polynomial. So I'm going to change my strategy slightly. In the interest of making the algebra happen at the level of the states. So this is an obvious thing to do after the fact. I'm going to label the circles with plus 1s and minus 1s. And then a circle labeled plus 1 will give me a Q, and a circle labeled minus 1 will give me a Q inverse. And then instead of having just the one circle, I have the two different possibilities for that circle, and each one contributes a monomial. So then the binomial theorem is happening in the states instead of in the algebra. You see, if you had two circles, you would get Q plus Q inverse squared coming out of them. But if you had all the different labelings of the two circles, you get the same thing. So this will circumvent having the binomial theorem happening in the powers of the algebra, and you will sum over many, many more things as a result. So the basis states for the Hilbert space are these same guys, but each one of them is labeled with plus or minuses and corresponds to a number of different basis elements. So there are 4 basis elements corresponding to that, and there are 8 basis elements corresponding to this. And that's the Hilbert space for the model that I'm going to work with. This just illustrates how I would evaluate one of them, right? I will get b cubed, which is minus q cubed, and then I get a 1, and a minus 1, so I get q squared, q inverse. And so I get the monomial q squared, q inverse, minus q cubed, corresponding to that state. So then, let's go back to the states for a moment. Then I can write the following pretty formula in the abstract for the bracket polynomial. It's just a sum of monomials, one monomial for each state. And of course, you have to think for a moment, well, what is the power of Q that's coming from a given state? It's contributed by the labeled loops, and it's also contributed by the smoothings. There's 2 different contributions to it. And there's a minus 1. And the minus 1 is raised to the number of B-type smoothings in the way we set it up. But it's a sum of monomials, one monomial for each state. So now we can do the following. We let C of k, I called it C of k with malice aforethought because it's going to turn into a chain complex. C of k denote the Hilbert space with this basis. Define a unitary transformation by multiplying by the coefficient for that state, letting Q be on the unit circle. Then it's certainly unitary. And the trace of U is equal to the bracket polynomial. as we reconfigured it. So therefore, we have a quantum algorithm for computing the Jones polynomial. And we have put the Jones polynomial into a quantum context. The polynomial has been, in a certain sense, replaced by a unitary transformation on a Hilbert space. And the Hadamard test that we described before, the test for finding the trace of a unitary process, could be applied to compute the polynomial. Of course, this is conceptually simple and computationally bad. I like it because it's a way of explaining how you go about making a quantum algorithm and putting something into a quantum context. But it isn't the way I would like to compute the Jones polynomial. It's much too long a process, much too simple a matrix. The matrix is just a huge exponentially sized diagonal matrix. Not interesting as a quantum algorithm, really, but interesting to see how you could formulate this. So that's a quantum algorithm for the Jones polynomial. Oh, by the way, it's the only quantum algorithm I know for certain generalizations of the Jones polynomial that have this form. So it also is a way of asking the question if you have some other invariant. For example, you can put the Alexander polynomial into a similar form, or you can generalize the Jones polynomial to virtual knots. And when you do those sorts of things, then I don't know another way. But here there is another way. That's the part that I decided not to talk about here, making braid group representations that give rise to the Jones polynomial. And you can make some very interesting braid group representations that will give rise to it. And again, you need to find the trace of them. So the basic form of the algorithm is the same. You would use the Hadamard test in the end. But the method of producing the matrices that correspond to the knot or the link are not as inefficient as this. So now I want to talk about Kovanov homology. And Kovanov did a remarkable thing. What he did was he showed how to associate to this polynomial that we've been looking at a homology theory, so that in a certain sense of grading, which you'll see in a moment, the graded Euler characteristic of this homology theory is the bracket. Well, we're going to see that the chains in this homology theory, if we worked over the complex numbers, is exactly the Hilbert space that I just described to you. But how does this happen? Well, try viewing this next slide as a category. Now, the slide is a picture of the 8 states of the trefoil knot, but I've organized them from left to right so that the state that's all A's is on the left, and if I make single smoothings on any of the sites in that state, I get to states with 1 B. If I then make single smoothings, I get to states with 2 B's, and finally I get to the states with 3 B's. So the states, and this is clearly can be done in general, you can organize the states from the ones that are all A's to the ones that are all B's and various states in between in such a way that there would be one generating arrow that goes between 2 states exactly when the 2 states differ by 1 smoothing, and the smoothing goes from A to B. So there is that pattern of the states. It looks like a cube, and abstractly it looks like this, a cube labeled with all A's at one end and all B's at the other vertex end, and in between A's and B's like that. As I said, I want to think of this as a category, and now let me say things in category language. If I had a functor from this pattern, these are just abstract objects, but if I could take a functor from this pattern to a category of modules, where this is a module and these diagrams commute, if I had a functor which took this into a module category, why then I could make a chain complex out of it by taking the alternating sum of these maps coming out of any one of these and calling that the boundary. And that would be a boundary map, where the different parts of the chain complex are this guy, then here's the next one is the direct sum of these modules in the vertical line, then the direct sum of these modules in the vertical line, and so on. Since the diagrams commute, you can see that boundary will be equal to 0. It corresponds to the diagram's commuting. So it's a categorical pattern that gives rise to some homology you could calculate if you could make modules that did that. So then Kovanov is thinking at that level of abstraction when he makes this structure, looking at the states not as just contributors to the polynomial, but as lifted up, as modules. And then how is he going to do it? How would you associate a module to this complicated bit of combinatorics and a module to this complicated bit of combinatorics? But if you have the idea, then the next part falls in almost naturally. There must be a module associated to a circle. Fine. So some module is associated to a bare circle. What would you associate to two circles next to one another? Well, it could be a sum or a product. So turns out it's product, tensor product. So you take the tensor product of the modules associated to these two circles, and that's the module here. Here you're going to have only one of them, only one here, but here you have tensor products, and here you have a triple tensor product. And then one smoothing from a collection of modules is supposed to give rise to a map of modules. How could that happen? Well, what's the minimal requirement? This I said before. The minimal requirement is that when you go by resmoothing from two circles to one, there should be a map of modules, V tensor V to V. And there should be a mapping from V to V tensor V corresponding to the other kind of smoothing. Now that looks like multiplication, and the other one looks like a co-multiplication. And so you need a structure like that, an algebra with a multiplication and a co-multiplication. Then some geometric thinking ends up convincing one that one should think of these as little cobordisms of surfaces. So when you go from one smoothing to the other smoothing, you're going through a saddle like that. And then the different mappings can be thought of this way. Multiplication is two circles melding into one. Co-multiplication is two circles splitting into two. And then various configurations of such surface cobordisms can happen. And multifold ones will be homeomorphic, as you see here. It turns out the right kind of algebra to use is one where all of the different homeomorphic surfaces that you would draw when you draw compositions of maps should give the same result, a topological quantum field theory in low dimensions. So these guys here would all have to give the same composite. One of them is delta, M composed with delta. The other one is, well, you can read it out. And the compatibility condition, in order that the diagrams would commute, in order to make the functor, remember you needed those diagrams to commute, it turns out to be that all these cobordisms work right. So there's a little bit of geometry of cobordisms of one manifolds in back of making the chain complex. But then the question is, can you make it? Is there a bit of algebra that will do that? And there are algebras that do that. And here's the one that Kovanov uses originally. Very simple algebra generated by two things, 1 and x. X squared is equal to 0. Delta of x is x tensor x. And delta of 1 is 1 tensor x plus x tensor 1. I'm not going to go into the details. But you see, that means that if you take a single loop and you label it with an x, that corresponds to one of the generators in that module. And a single loop generator labeled with a 1 corresponds to the other generator. So two labels on a loop turn out to be useful here. They can correspond directly to Kovanov's generators. So our minus 1 is going to correspond to the x, and the 1 is going to correspond to the plus 1. And now the Hilbert space that we created before can be regarded as having as its basis the generators of the chain complex. Right, it is the generators. Think of a collection of loops, like 3 loops. And one of them is labeled x, and the other is labeled x, and the other is labeled 1. So that's the generator x tensor 1 that would happen in that tensor product. So our chain complex is the Kovanov chain complex, and the boundary mapping has been defined by us, but in order to see how it works, you would have to go back and look at this. For example, in the boundary here, this might be labeled x, and that might be labeled x, in which case the boundary mapping would be 0 on this part, the local boundary mapping. But if this was labeled, because x squared is 0, But if this is labeled 1 and this is labeled x, then under boundary, this ends up being labeled x. You have to be able to answer the question for things labeled x and 1, what happens to them when you take the boundary? And you can get some superpositions, some linear combinations. Here, for example, if this was labeled 1, then under delta, we get this, 1 and x, plus x and 1, a sum of two things in the chain complex. The fact that you get the sums means that interpreting this chain complex as a space is going to turn out to be tricky and difficult. It's not quite a space. So that's the picture of the Kauffman homology. That's how it's constructed. And now let's go back to the polynomial. Oop. Actually, that's a good idea. I'll skip that slide. Let's go back to the polynomial. Oh, didn't want me to skip the slide. All right, you know, we had the polynomial written in terms of the enhanced states. There it is. And the J is the number of B smoothings and the number of plus Q's and minus Q's. We can collect the states up. We could say there are those states that have a given I and a given J. And that's a subspace of the Hilbert space. And the dimension of that subspace multiplied by that particular monomial is another way of expressing the bracket. But now, what am I going to tell you? I'm going to tell you that the Cij is actually the grading for our homology. That what happens is that when you apply the boundary, the I goes up by 1, and that's because the number of B smoothings went up by 1 when you smoothed. But the J remains the same, which is something that you'd have to puzzle out, and I won't show you explicitly, but it's true. The J remains the same. That means that we didn't just get one chain complex, we got one chain complex for each power of Q. And each one has its own homology. And when we collected everything up this way, we could recollect it a little further. I hope it's on the next slide. Yes, I can recollect a little further by taking all of the i's together and leaving a fixed J. And that is an Euler characteristic of that sub-piece of the homology. This jth piece is in itself, in its own right, a homology generating chain complex. And it has an Euler characteristic. And so and of course, everything is homological here. The Euler characteristic of the chain complex is equal to the Euler characteristic of its homology, the alternating sum of the dimensions of the homology groups. So in the end, we get that the bracket polynomial is equal to the sum of the powers of J, Q to the J, times Euler characteristics of the homology, each jth homology. So that's the graded Euler characteristic statement about the Kauffman homology. I should mention before leaving it that there's a non-triviality in here that is really a kind of intense and needs to be understood better. And that is why this homology is an invariant of the knot. What I told you about, with some indication of how you do it, is how you make sure that there is a homology, that the chain complex has d squared equals 0. But to show that this whole structure is an invariant of the knot, that when you move the knot around by Reidemeister moves, the homology remains invariant for this choice of the Frobenius algebra. That's not obvious and requires proof, and all the proofs are a little tricky. So it would be good to understand better what's going on here. And it exacerbates a question that's been around for a long time, which is how do you understand the Jones polynomial in a topological way? For which there are some answers that come from Witten and so on. But one would like a definition of this kind of homology theory that has the nice invariance built in right from the beginning, like singular homology or something, but we don't know it yet. So that's what it looks like. The states of the bracket polynomial get up-leveled into specific directions in a Hilbert space in this picture, into generators of a chain complex in that other picture. And we have this. And we also have this. If you look back at the boundary, in relation to the unitary transformation that we described, you see that the u delta plus delta u is equal to 0. You see easily that from the boundary definition that we made, which means that the unitary transformation corresponding to the Jones polynomial actually acts on the homology. And it acts on the individual states as eigenvectors, and so at least you can make a description like this, that the chain space is the sum of eigenspaces, and that the bracket polynomial is the sum of eigenvalues times the Euler characteristics of the homology of the eigenspaces. Now, all of this description is, as I said, can be regarded as a description of a partition function that is particularly good for knot theory, but can be thought of as a description of the partition function of the Potts model in a certain sense. So in what sense? We've got a couple of minutes left. Let's jump there. The questions are clear, so I'll just jump to the Potts model. I'm going to give you a very quick description of the Potts model. You'll see why the Potts model is so closely related to this. But first, for statistical mechanics, the partition function is the sum of the exponentials of, let's say j is minus 1 over kt times the energy of the state. That exponential is supposed to be the proportional to the probability of being in the given state, where state here is the state of the physical system. T is temperature. In the Potts model, you have capital Q numbers of local states. And the energy is the number of edges in the graph where the endpoints of the edge receive the same label. That's how you count energy in the Potts model. So that means, if we're thinking about this particular model, it means that if you're at 0 energy, you've colored the graph according to the graph theorist's specifications of coloring. If two vertices are connected by an edge, they're colored differently. So 0 energy is graph coloring a la graph theory. And above that are all the different ways of throwing colors on the graph which don't necessarily satisfy the graph theorist. Q equals 2 is the Ising model. There's a very nice result about the Potts model, which due to Temperley, which says that it can be calculated by a graph polynomial. And the graph polynomial is the dichromatic polynomial, which I've illustrated abstractly here. For Q colors, it satisfies that if you take an edge in the graph and delete it or contract it, then the polynomial is the sum of what happens when you delete it plus v times what happens when you contract it, where v is some other variable. So you have two variables, q and v. The result is that if you let v be equal to that exponentiated energy term for one bit of energy, e to the j 1 over kt minus 1, and compute the dichromatic with that v, that gives you the Potts model. That's Temperley's nice result. We might take a moment. No, I don't think we even have a moment, but you can easily see why it works by thinking about it or doing an example and then thinking about it. But the association that gets us over to the bracket is the medial graph. You start with your graph and you put a little x on each edge of the graph and then connect them up, and you get out of a graph, a planar graph, a knot or link diagram. Like in this case, we got a figure 8 knot out of that graph. You conventionally choose all the crossings to be the same with respect to the edge. So you get a graph and you get a colored graph. If you look at the colored graph in relation to the graph polynomial, you see that deletion and contraction correspond to the two ways of smoothing. And so now it's almost completely clear what's going on here in terms of the relationship. And you have to do some translating because here are shaded regions and there in the bracket calculation are boundaries of regions. But the result is that you can write down a bracket just counting boundaries of regions that does the same job by multiplying by something different in the contraction aspect, q to the minus 1/2, and taking the loop to be q to the 1/2. And then it will give you the Potts model up to a power of q. So you can calculate the Potts model by using a bracket, but it isn't necessarily topological. So now we can actually compare we can say, well, let's suppose, to keep things simple, let's suppose it's topological. Let's suppose that the q to the minus 1/2 v is actually equal to the minus little q for the topological case, and that the capital Q to the 1/2 is q plus q inverse. I'll stop for a moment. Sorry, I wanted to do this picture. So sorry. All right. This is a picture of the medial. It should have been in, a little earlier. And a graph. Here's a graph. There's the medial. And now you see how various regions of constant spin pictures correspond exactly to the bracket states. Now, one thing I can do is I can add an extra parameter, which I did here, and call it minus q rho, and then it shifts it out of topological depending on the value of rho. If rho is 1, we're topological. And then we want to match it to a Potts model, so we match it and compute and find out about the temperature. Our q is an integer, so you can't do everything. And our question is, what does this tell us about the Potts model? And we find out, among other things, if the rho is off-center, then we won't be getting Euler characteristics. We're getting sort of deformed Euler characteristics. But if the rho is 1, we will actually get the same story we had before, because we will be in the combination of topological and Potts. But that combination, you can do a little algebra and check it out. I just want to get the last slide. The algebra is obvious. What you do, substituting. But what you end up with is that when you can say the nice picture of the Potts partition function as a sum of q to the j times Euler characteristics of things, you're at imaginary temperature. So that's where I stop now, but I want to look at it further, because certain imaginary temperature models of the Potts, certain imaginary temperature situations in the Potts model have this nice Kovanov homology interpretation. And the question is, does it tell us anything about the Potts model at real temperatures? By asking, how do imaginary temperature values for the Potts model affect its real values? And I don't know the answers to those questions. So we only ran 5 minutes over. I'll stop.
Yes, Misha.
I'll ask you. I have a question or remark which I combine because you consider different topics, and the last I know a little bit better than all others. First of all, the main problem in your whole discussion is how to relate quantum mechanical systems with classical, because nodes is classical object, is trajectory in ordinary space. And only one way to do it is to relate with some diagrams of nodes, what you more or less thought. And one suggestion. For example, we know in Ising model, it's analytical solution of Unsider.
Right.
Is it possible using your technique to obtain this solution? It will be good examples of this efficient.
Well, no.
I finish and
right,
then you answer.
right.
No. The second, what about Potts model? It's the same question, but in this theory, what I know and I work to not only abelian, non-abelian case, it is famous Kramer-Svanier duality, which is possible to generalize in all this. It will be interesting to compare this, because this is very efficient method to find phase transition points. Mm-hmm. Because all with your technique is, in some sense, it looks that it's one interesting point, another interesting point. But really, it's, I guess, what Kovanov homology really not help us to find, for example, phase transition point in Potts model for example, for 4 states or 3 states, or at least maybe 2. Mm-hmm. So this is my question, is about relations between real physical applications and general not
correct.
ideas.
Yeah, so-
and
so-
the last,
so-
the main question is what how classical.
Yeah, my questions exactly. Those are my questions exactly. But the point about Wiener's-Kramer duality is a good one. We aren't trying here to get at the limit of the models. Notice that I'm talking about how it behaves on finite graphs and the patterns of that. But nevertheless, there might be a way of using the knot theory to get at the limit of the model. But I'm not trying to address that here. I really don't know. So that part of a possible application is still wide open. One has had this kind of translation around for a long time, and it's not obvious how to deal with that. The other thing is, I guess I should warn you again that I deliberately talked about the quantum mechanical model. It's one subject, and the Potts model is another subject. I could have said, you'll notice, that here's the Kovanoff homology, the way it's defined for knot theory, not using any quantum context at all, and this fits into the Potts model in this way. On the other hand, the fact that we're getting the Potts model at imaginary temperatures suggests that we're actually talking about quantum mechanics, not about the Potts model for these values where the thing works nicely topologically. So there are a lot of questions. It's not obvious how, at the moment, it's not obvious how to make it tell you something honest about the Potts model itself. We'll see. Yeah.
At the start of your talk, you said knots are contextual. And did you mean contextual in the sense of Cauchy-Zwicker? You mean that sort of measurement contextuality?
Something like that is in the back of my mind, but when I was mentioning knots as being contextual, I was talking about knot theory itself as the placement problem, right? Knot theory is about how is one space placed in another, and that is a contextuality problem. But the other problem is related to what you said. One can ask, how is topological entanglement related to quantum entanglement? And some people have suggested that that you should make the comparison directly, in the sense that if I probably better to draw something. Chalk. Well, never mind. Think of the Borromean. Oh, there they are. Well, but never mind. Think of the Borromean rings, right? If you were to take any one of the rings away, they fall apart. So the Borromean rings are triply entangled, but not doubly entangled in any way. If I form the quantum state, the GHZ state, 0, 0, 0 tensor 0 tensor 0 plus 1 tensor 1 plus tensor 1 divided by the square root of 2, then if I measure it, I go into, no matter how, and measure it in any one of its tensor factors, then I end up with an unentangled state. So the GHZ state looks like the Borromean rings. This is a remark due to Aravind. So Aravind suggested that maybe we should compare topological entanglement with quantum entanglement in this kind of direct way, where measurement means removing one of the links in a link. But it's kind of too superficial to do anything other than make formal comparisons. And one would like to know if there is something deeper about the interrelationship between topological entanglement and quantum entanglement. And I think you do have to go deeper. You have to go to some place about space that is talking about the source of what happens when you get topological contextuality and when you get quantum contextuality. In quantum contextuality, you are breaking the space into a measurement part and a part that's measured. And then within that, certain restrictions start to occur. And the non-locality is present to begin with, in a certain sense, because all you know is that measurement is happening here, and the rest of the space is up for grabs probabilistically. So somehow that kind of contextuality about the creation of spatial entities, and the other one that happens in the knot theory, which is much more classical, the space is given, certain specific things in the space are given should be compared. So indeed, I'm very interested in how to make that comparison, but I only play with different models of it that don't quite mesh.
Samson Abramsky has recently written these papers on sheaf theory and non-contextuality, where non-contextuality is, it comes up as the non-existence of a global section of a sheaf. Right. But it's, so I mean, that's one form of like topological, non-contextuality, but it's not obvious how it relates to what you say about knots, yeah.
Right, good. Maybe I get a reference from you about that sheaf theory.
Any other comments? Well, I think we're all entangled to some extent, some part or other of the lecture, which covered an amazing range of ideas. Thank you very much, Lou.
Thank you.